Good morning class. In this session we will discuss about non-polar covalent compounds. In the last segment we discussed about polar covalent compounds, in which we saw examples of water and example of other compounds. We saw HCl we saw as an example. But in this segment we will discuss about non-polar covalent compounds. So what are non-polar covalent compounds? Let us discuss first non-polar covalent compounds. Non-polar covalent compounds. What are these? Let us discuss. Now, the non-polar covalent compounds, the first thing which is responsible for polarity of covalent bond is the charge separation. In the last example of polar covalent compounds, we saw the process of charge separation. Charge separation was a process wherein the more electronegative atom was attracting the shared pair of electron. As a result, there was high concentration of electron on the more electronegative atom and a less concentration of electron on the less electronegative atom. So this repulsion or this separation of electron cloud was termed as charge separation. So the first most thing, in non-polar covalent compound, there is no process of charge separation. Second thing, in non-polar covalent compounds, if we see examples, all the homoatomic molecules are the examples of known non-polar covalent compounds. Homoatomic molecules mean that both the atoms which are forming the molecule are of the same nature. Like for example, we have H2, O2, N2, Cl2. All are these examples of homoatomic molecules, because in hydrogen both are hydrogen atoms, in oxygen both are oxygen atoms, in nitrogen both are nitrogen atoms, and in chlorine both are chlorine atoms. So the most important thing is all the homoatomic molecules are non-polar covalent compounds. It is because, like we see example of what hydrogen, that is H, single bond H. In this case, both are hydrogen atoms and both will have equal value of electronegativity. So the pull created by this hydrogen will be equal to the pull created by this hydrogen. Means the two forces are equal and in opposite direction. So in such case, the electron cloud will remain its own place. There will be no change in electron cloud, and as a result, it will behave as a non-polar covalent compound. So we studied 2 points about non-polar covalent compounds. First one is there is no process of charge separation, and the second thing, all the homoatomic molecules are always non-polar covalent compounds. For example, hydrogen, oxygen, nitrogen, chlorine. But there are two more examples which are not homoatomic, but they are non-polar covalent compounds. And they are, one is example of carbon tetrachloride, CCl4, and the other is the example of methane, CH4. They both are not homoatomic, but still they are non-polar in nature. So let us see the reason why they are non-polar in nature. First we will see the example of CCl4. If we discuss about the structure of CCl4, this is the structure of CCl4. In between we have central carbon atom, and the 4 chlorine atoms are linked in such a way as shown by this diagram. So, if we discuss about this bond, in this bond, if we consider this bond, then in this bond, this chlorine atom is more electronegative compared to this carbon atom. So, this chlorine will attract the shared pair of electron towards itself. The same will happen on this side, same will happen this side, and same will happen this side. So if we consider this bond, these two bonds, this one and this one. So both chlorine atoms are exerting same force and in opposite direction. So because they are exerting same amount of force and in opposite direction, so both the forces cancel each other and there is no movement of electron cloud of carbon atom. Again, the same thing happens in upward direction and downward direction, and same thing happens in left and right direction. Again, the force exerted by upward chlorine is equal to the force exerted by downward chlorine. Again, the two forces are equal and opposite in direction, so they again balance each other and the electron cloud of carbon remains unchanged. So, carbon tetrachloride is an example of non-polar covalent compound. The same thing happens with methane. We have carbon atoms in central position. This is one hydrogen, this is second hydrogen, this is third hydrogen, and this is fourth hydrogen. Same thing happens. The electron pull created in all the four directions, again same reason. The force exerted in upward direction is equal to the force exerted in downward direction. The force exerted in right direction is equal to the force exerted in left direction, just because all the forces counterbalances each other. That's why it is again an example of non-polar covalent compound. So today we are discussing about non-polar covalent compounds. The first thing about non-polar covalent compounds is there is no process of charge separation, and the second thing is all the homoatomic molecules are always non-polar covalent compounds like hydrogen, oxygen, nitrogen, chlorine, etc. But there are two exceptional cases which are non-homoatomic, but still they are non-polar. First one is example of carbon tetrachloride CCl4, and the second example is of methane CH4. If we see the structure of CCl4 carbon tetrachloride, in between we have carbon atom and 4 chlorine atoms attached at 4 locations, one above, one below, and one on right side and one on left side. The force exerted by this chlorine in right direction is equal to the force exerted by chlorine in left direction. Again, the force exerted by chlorine in upward direction is equal to the force exerted by chlorine in downward direction. So the net force acting on this carbon atom is 0. Hence, it behaves as a non-polar covalent compound. Again, in case of methane, we have carbon atom in central position and 4 hydrogen atoms attached in the same way as we had chlorine atoms in case of carbon tetrachloride. So in this example also, the force acting in all the 4 directions counterbalances each other, and since the forces counterbalances each other, again this methane is also an example of non-polar covalent compound. So this we already discussed about polar covalent compounds. This was the case with non-polar covalent compounds. Now, next topic is we will discuss about the representation of covalent compounds. Next topic is representation of covalent compounds. How we can represent formation of covalent compounds. So in this case, we will discuss two categories or two types of representations. The first representation is electron dot representation or electron dot diagram, electron dot structure. and the second is electron orbital diagram. So these two types of representations we have to discuss in case of covalent compounds. So let us discuss the first one, electron dot structure. Electron dot structure. We will see the first one, that is electron dot structure. Now, when we are discussing about electron dot structure, again we are going to represent only the outermost electron which is present in an atom again. So we will see many examples, like we will see the case of chlorine, nitrogen, oxygen, fluorine, hydrogen, etc. We will see. So let us see the first of all and discuss one by one of them. So first we are going to draw the covalent representation of or covalent bonding representation in chlorine. So in case of chlorine, we have two chlorine atoms. And both the chlorine atoms are having 7 electrons in their outermost shell. So we are going to represent the electrons by crosses. These are the 7 electrons of this first chlorine atom. And again we are going to have 7 electrons of the second chlorine atom. Since both of them need one more electron to attain octet, so they will share one electron, and hence a single bond will be formed between them, and hence it will lead to the formation of chlorine molecule. This is our chlorine molecule. Second case is of nitrogen. We have 2 nitrogen atoms, and both the nitrogens are having 5 electrons in their outermost shell. So we are going to represent the 5. Again, both the nitrogen atoms need 3 more electrons to attain their octet. Both the nitrogen atoms need 3 more electrons to attain their octet. Hence, they will share 3 electrons each. As a result, a triple bond will be formed between the 2 nitrogen atoms, and this will lead to the formation of nitrogen molecule. So first was case with chlorine, second was the case with nitrogen. So in case of chlorine, we have 2 chlorine atoms, and each chlorine atom need one more electron to attain their octet. So both the chlorine atoms will share 1 electron each. As a result, a single covalent bond will be formed between the 2 chlorine atoms, and hence they will be converted into chlorine molecule. Now the second is the 2 nitrogen atoms. They are having 5 electrons in their outermost shell, and they need 3 more electrons to complete their octet. Hence, both the nitrogen atoms will share 3 electrons each. As a result, a triple bond will be formed between the 2 nitrogen atoms, and hence this leads to the formation of nitrogen molecule. The next is case with oxygen. Next is the case with oxygen, O2. In oxygen, we have 2 oxygen atoms, and each oxygen atom has 6 electrons in the outermost shell. So we are representing the 6 electrons by 6 dots, and each oxygen atom needs 2 more electrons to complete its octet. So they both will share 2 electrons each. As a result, a double bond will be formed between the 2 oxygen atoms, and this leads to the formation of oxygen molecule. This leads to the formation of oxygen molecule. Next is the case with fluorine, F2. In case of fluorine, we have two fluorine atoms, and each fluorine have 7 electrons in their outermost shell. So I am representing the 7 electrons by 7 crosses, and the same configuration will be present for the next fluorine atom. So both the fluorine atoms need 1 electron more to complete their octet, and hence they will share 1 electron each, and as a result a single bond will be formed between the two fluorine atoms, and this leads to the formation of fluorine molecule. Okay, so thank you.